We'll continue our discussion of electrophilic aromatic substitution with the halogenation of benzene, and much like the nitration of aromatic groups like toluene and benzene and other substituted phenyl groups, we first have to start by generating a very powerful electrophile which can react with the double bond in a benzene or a toluene or a similar molecule. So just looking at the generation of the electrophile, if you have an aluminum halide, like aluminum chloride, then the traditional way to draw its dot structure is like such. Where the aluminum clearly has an empty orbital because there's only 6 electrons in its environment. And if you go ahead and draw the aluminum with the double bond to a halogen, such as chlorine in this case, it could also be a bromine or an iodide. So aluminum chloride, aluminum bromide, or aluminum iodide. If you go ahead and draw the double bond, then we have a little problem with the formal charge, that you have a plus on the chlorine and a minus on the aluminum. And given that chlorine is far more electronegative than aluminum, you would not expect this to be the case. In reality, the aluminum chloride, unless it's dissolved, is going to have an ionic structure, more of an ionic structure, where the aluminum is surrounded by probably 6 chlorides, and they pack in. But the exact structure of the aluminum chloride, we don't really need to worry about right now. We'll just treat it in a simple sense, as if aluminum is bonded to 3 chlorines, then it's got an empty orbital. And whether you can displace the double bond or separate a polymer of aluminum chloride doesn't really matter. The effect is the same, that if aluminum chloride were to react with chlorine, you'd have a nice straightforward acid-base kind of reaction. Again, Lewis acid-base reaction. So because this has an empty orbital, that's going to make it a Lewis acid, which is an electron pair acceptor. So if you take a chlorine off of the chlorine molecule, and its lone pair of electrons would make it a Lewis base. So this Lewis base can go and react with the Lewis acid. The non-bonding pair of electrons on the chlorine will become a bonding pair of electrons and make another chlorine attached to the aluminum. And a really important thing in this mechanism is that the bonding pair of electrons in the chlorine molecule will go with the chlorine that's being taken by the aluminum. So when we go ahead and do this reaction, we end up with the aluminum bonded to 4 chlorides essentially, and some might call this tetrachloroaluminate. But this is an anion. And the other thing that you would get, if you take electrons away from this chlorine, like that, then you get a chlorine cation. So since the electrons would have been removed here, that gives you a chlorine that's formally and truly positive. So if you were able to take a chlorine ion, chloride, away from the chlorine molecule, you would be left with a chlorine cation. And that is going to be your powerful electrophile. So essentially the aluminum chloride is a catalyst that participates in this reaction by activating the chlorine molecule for reaction by creating this Cl plus electrophile. So this is actually a lot simpler than the generation of a NO2 plus electrophile. And if you understood the next part, where we went ahead and did the substitution reaction, then the substitution of the chlorine here, the chlorine cation, for a hydrogen in benzene will be fairly straightforward. So let's go ahead and take a look at that. if you have benzene, C6H6, I'm going to draw out all the atoms, even though the skeletal structure would make it a lot quicker and easier to do. Benzene, C6H6. And if this reacts with a chlorine plus, right, so this is a chlorine with a positive charge, this is going to be very much an electrophile. Chlorine is very electronegative, loves electrons all by itself. If you've got a chlorine that's positive, it's so electron deficient, plus naturally loves electrons, it's like a super electrophile. And that's why it attracts the electrons in the double bond of the benzene to bond to it. So if you follow along, this pair of electrons that was a double bond between the two carbons is now going to form a single bond between a carbon and a chlorine. So now your benzene becomes less benzene-like because we just went ahead and took away one of the pi bonds to form a sigma bond to the chlorine. The carbon that had the chlorine has the chlorine on it now, also has a hydrogen on it. And then the other carbon that used to be involved in the double bond is now carbocation. The rest of the molecule, the other 4 carbons, have just been sitting there and watching. So this little area over here, we just copy over. But this double bond area, we had the chlorine cation come in and bond to a carbon using the pi electrons that used to be the double bond. And as those electrons get pulled away from this carbon, it becomes a carbocation. And as before, we might expect some nucleophile to go in and get the carbocation, but it doesn't work out that way. We're going to reform that double bond. We added in the chlorine plus. We're going to now remove an H plus. So the thing that is kicking around that would be a modest base and be able to get that H plus off is this tetrachloroaluminate. A big old minus there. And so one of the chlorines and here is going to take its lone pair, go pluck off this H plus, and that allows us to reform the pi bond. And so rather than having benzene with 6 hydrogens on it, we have chlorobenzene, which will have 5 hydrogens. And we just added a chlorine in the place of one of the hydrogens. So again, substitution, it's really important to keep the name straight. This was electrophilic aromatic substitution. This 6-membered ring with the 3 double bonds is the aromatic group. We needed a potent electrophile to kick in the reaction. And it's a substitution, meaning we add in one atom and take something else off. So we substitute. This carbon that used to have a hydrogen on it now has a chlorine on it, and we have reformed the double bond that was temporarily not part of the molecule. And then what we end up having as the other product is the aluminum chloride, it's essentially now bonded to a hydrogen. So people write this one very differently, and that's something that I think depends on their detailed understanding or how much they look for technical accuracy. Some people would write it HAlCl4 as the acid that's an H plus with an AlCl4 minus. So this is one good way to write this formula. Other people write it's essentially an adduct of adduct, ADDUCT. Adduct might be a new word for some people, between the aluminum chloride, and HCl. So these two are associated with each other. The details of how it exists in solution might depend on the solvent, it may precipitate, etc. I haven't run this reaction in a long time, so I'm no expert in what you would see or what you would, where the product would end up at this stage. But the substitution reaction, adding in the electrophile to form the intermediate, then deprotonating the intermediate to form the substitution product. So pretty nice there, and that gives you the overall substitution. So as usual, any questions about these mechanisms, make sure you just go over and rewrite the mechanism yourself, making sure that you get each step right and you pay very close attention to what you're saying the electrons are doing. So like this pi bond here, it's a pair of electrons that goes and bonds to the chlorine, making a sigma bond where there used to be a pi bond. The other thing that's important here is this is a general reaction. So the halogenation can be a chlorination, like we just showed. It could be a bromination if we used aluminum bromide and bromine, and it could be an iodination. I don't know if I've ever heard that word before, but that's the power of this. Understanding the concepts of the science is if you can chlorinate and you can brominate, then you can iodinate. So we can even make up our own words we've never heard before, and people will understand what we mean. So again, changing the nature of the halogen changes the product in a systematic way. So I hope this was nice and clear and informative. If you have any questions, feel free to send me an email or contact me in the usual ways.